The order given in the last days of December 1864 is not a command to engage the enemy. It is a command to destroy the vessel. The Confederate ironclad Georgia is not sinking due to Union cannon fire or a ramming collision. She is being murdered by her own crew. General William Sherman is closing on the city of Savannah, and the Naval Command has determined that the ship cannot be allowed to fall into federal hands. The physics of the decision are absolute. The vessel lacks the engine power to retreat upriver against the current, and she is too slow to escape to the open sea. She is a fortress trapped in a river of mud. The crew works fast to deny capture. They disable the massive Dahlgren guns to render them useless. Then they scuttle the vessel. The river rushes in, and the ironclad settles to the bottom. She does not capsize. She simply settles into the darkness of the Savannah River, roughly 36 feet down, taking her armor, her guns, and her ammunition with her. For the next century and a half, she sits there, not as a ship, but as a hazard to navigation, a jagged pile of iron and timber waiting in the dark. To understand why this specific wreck poses a unique threat to modern engineering, one must understand her origin. The Georgia was never a standard warship. She was built in 1862 during a desperate shortage of rolled iron plate. Her construction was funded by a donation campaign led by the women of Savannah, earning her a nickname tied to the Ladies' Gunboat Association. But the fundraising could not buy materials that did not exist. Instead of proper armor plate, her builders used what was available, which was railroad iron. They took long T-rails and spiked them in alternating interlocking layers against a thick timber casemate. It was an improvisation of immense weight. The resulting structure was so heavy and her steam engine so underpowered that she could not effectively maneuver in the tidal currents of the Savannah River. She was classified not as a ram or a cruiser, but as a floating battery. She was a stationary island of iron designed to guard the channel until the moment she was scuttled. In the 21st century, the logic of the river has changed. The port of Savannah is one of the busiest container terminals on the eastern seaboard, but it is constrained by depth. Modern post-Panamax container ships can draw close to 50 feet when fully loaded to navigate safely. The existing shipping channel is too shallow. The Savannah Harbor Expansion Project is authorized to dredge the river bottom to a depth of 47 feet to accommodate global commerce. This engineering mandate creates a binary conflict. The Army Corps of Engineers cannot dredge the channel until the wreck is removed. Yet the wreck is a protected archaeological site governed by historic preservation rules. The Georgia sits on the edge of the navigation channel with her upper works protruding into the required depth envelope. She is a hard iron fowl in a soft mud river. The problem is not simply lifting an old boat. The problem is what remains inside her. When the ship was scuttled, much of her ordnance remained in and around the wreckage. The wreck site is a field of unexploded ordnance scattered across the bottom. There are rifled shells, cannonballs, and stands of grapeshot, all entombed in anoxic mud since 1864. The site is effectively a flooded ammunition depot. A standard dredging cutter cannot simply chew through this debris field. If a dredge head strikes a large live projectile, the result could be catastrophic damage and loss of life. The removal operation, therefore, cannot be a brute force excavation. It must be a surgical extraction performed under the most hostile conditions imaginable. The mandate is clear. To reach the authorized channel depth, the Georgia must be cleared from the channel footprint. The obstruction has to be removed, documented, and mitigated without turning the site into scrap. The operation requires a collision of two very different disciplines. It requires the delicate documentation of underwater archaeology and the heavy industrial lifting of marine salvage. The engineers must design a plan to dismantle a vessel that was never meant to be taken apart. They must lift sections of iron weighing tens of tons without disturbing live hazards hidden beneath them. The timeline is compressed and the stakes are economic and historical. If they fail, the port expansion halts. If they make a mistake with the ordnance, the cost is measured in lives. The river has held the ship for 150 years, but the modern world is coming to claim the channel. The engineers look at the survey data and realize that the hardest part of the mission will not be the weight of the iron. It will be the inability to see it. In this sector, the river erases sight before a diver even reaches the bottom. In the main shipping channel of the Savannah River, the water is a suspended solution of mud and runoff. Light from the surface penetrates only inches before scattering into nothingness. The divers from the Navy Mobile Diving and Salvage Unit 2 enter a world of absolute monochrome darkness. They call it black water. It is an environment where optical sensors are nearly useless and where a diver cannot see the pressure gauge on his own wrist. The river moves with a hard tidal current that turns water into a heavy kinetic force, constantly trying to peel the diver off the bottom. To work in that flow, a diver must carry heavy weight just to remain in place. They do not swim. They crawl across the riverbed using their hands to pull themselves along a guideline staked into the mud. The target zone lies at a depth of 40 feet. This is not deep by oceanic standards, but the conditions make it technically extreme. The wreck of the Georgia has been eroding for 150 years, and the river has buried the remains in silt. The wooden casemate that once supported the armor has disintegrated entirely, leaving the heavy iron rails to collapse into a chaotic pile. There is no ship outline to follow. There is only a debris field of jagged metal and rotting timber concealed in the sediment. The salvage team must map this chaos before they can remove it. Here, optical cameras buy them almost nothing. The team leans on sonar tracking and hard-earned touch work. It becomes a job for gloved fingertips. This technique is known in the industry as touch diving. It is a slow and deliberate process of tactile survey. The diver descends to the bottom and locates a preset grid line. He extends his arms and sweeps the mud in front of him, feeling for anomalies. He builds a mental map of the wreckage 1 square foot at a time. He must distinguish between a harmless log, a piece of railroad iron, and a jagged section of torn plate that could sever his umbilical. The diver communicates his findings to the surface supervisor by voice describing the texture and geometry of every object he encounters. The surface team plots these contact points on a digital chart, slowly constructing a wireframe image of the wreck from thousands of individual touches. It is a process of assembling a jigsaw puzzle in a dark room while wearing heavy gloves. The physical toll of touch diving in a 4-knot current is immense. The diver is fighting drag every second of the bottom time. The water presses the mask against the face and vibrates the regulator in the mouth. The sensory deprivation creates a specific psychological pressure known as the isolation effect, where the mind begins to detach from the orientation of the body. The diver must trust his depth gauge and his tender to know which way is up because his eyes tell him nothing. In this black void, the sense of touch becomes hyperacute. The fingertips search for the characteristic shape of the railroad T-rails that form the armor of the battery. They feel for the smooth curve of the cannon barrels. They trace the sharp edges of the broken casemate, trying to determine where one section ends and another begins. The survey reveals that the Georgia is not a single coherent mass. The collapse of the wood has left the iron armor in disjointed sections, some lying flat, and others pitched at steep angles. The mud has filled every void, creating a heavy suction that will resist any lifting attempt. But the divers find something else in the grid. Scattered among the heavy rails and the timber fragments are hundreds of smaller spherical objects. They are smooth and heavy, and they are resting in the silt exactly where they fell in 1864. The divers run their gloved hands over the curvature of the objects and realize that the debris field is not just scrap metal. The bottom is paved with the unexploded rounds that were meant to defend the city. The salvage mission has just become a bomb disposal operation. The inventory of the river bottom yields a specific and terrifying number, 185. That is the count of munitions removed from the debris field of the Georgia during the recovery effort. And within that haul, 170 large projectiles had to be rendered safe before heavy work could continue. In the world of marine salvage, a single live round is a critical hazard that can halt operations. In the Savannah River, they are working inside the flooded stockpile itself, scattered and buried by time. After generations in anoxic mud, the iron casings are corroded and the fuses are compromised and unpredictable. The powder within cannot be assumed inert. It has to be treated as live. The task of clearing this minefield falls to the United States Navy explosive ordnance disposal technicians. These are the specialists who combine the disciplines of diving with the physics of demolition. They enter the black water with a mandate that allows zero margin for error. The objects come to them by feel alone. A diver crawling along the guideline reaches into the silt and feels a curved, hard surface. He must determine by tactile inspection alone whether he is holding a piece of scrap iron, a rock, or a 60-pound artillery shell. The identification process is purely geometric. The fingertips trace the circumference looking for the fuse pocket or the driving band of a rifled projectile. If the object is confirmed as ordnance, the diver does not simply pull it from the mud. He must excavate the silt around it, gently freeing it from the suction without striking the fuse against the hard debris of the wreck. This is the first phase of rendering live ordnance safe. It is a discipline of extreme restraint. The diver is working blind in a hard current with devices designed to kill him. Each item is recovered under controlled procedures and stabilized under the direction of explosive ordnance disposal technicians. The goal is simple: remove the explosive teeth of the Georgia without triggering them. It is a systematic disassembly of the ship's offensive power. By the time the ordnance phase concludes, the wreck has been systematically defanged. The risk of a catastrophic detonation during dredging is neutralized. However, the removal of the shells reveals the true scale of the structural problem. With the mud cleared away and the explosives gone, the engineers can finally assess the armor that protected the battery. They find that the hull is not a standard naval construction. It is a chaotic interlocked puzzle of heavy iron rails that defies standard lifting geometry. The bombs are gone, but the iron tomb itself is the next adversary. The most dangerous aspect of the Georgia is not the explosive charge inside the shells, but the structural deception of her armor. To the casual observer or the historian looking at blueprints, she appears to be a standard ironclad vessel protected by a solid shield of metal. The reality on the river bottom is a geometric trap. The armor of the floating battery was not forged as a single coherent sheet of steel. It was assembled from hundreds of individual components that were never designed for naval warfare. Cut off from rolled plate by the blockade, the Confederate engineers turned to railroad T-rails. The design relies on a specific configuration known as interlocking rail armor. The builders took railroad T-rails and spiked them onto the wooden casemate in alternating orientations so the flanges nested and locked. It created a layered wall of iron backed by thick timber, a brutal improvisation born of shortage and local fundraising. Heavy, yes, formidable, yes, but no armor is truly invulnerable. However, in the 21st century, the physics of this design have inverted. The wooden timber that served as the spine of the armor has rotted away completely. The iron spikes that pinned the rails to the wood have corroded into dust. The interlocking rail armor is no longer a solid shield. It is a house of cards made of heavy iron bars. The rails are resting on top of one another, held in place only by gravity and the pressure of the surrounding mud. There is no structural integrity. If a salvage diver attempts to rig a strap around a section of the wreck, the pressure of the lift could cause the entire stack to slide apart. A single 24-foot rail weighing hundreds of pounds could slip free and crush a diver or sever a hydraulic line. This presents a paradox for the recovery team. Standard marine salvage relies on the structural continuity of the ship. Usually a salver will weld lifting eyes to the hull or pass chains beneath the keel to cradle the vessel. On the Georgia, there is no hull to weld to and no keel to cradle. The wreck is simply a pile of loose components that must be lifted as a unit to satisfy the archaeological mandate. The engineers cannot disassemble the armor piece by piece underwater because the interlock is too tight and the visibility is zero. A diver cannot see to unstack the rails, and the risk of a collapse is too high to work inside the debris field. The problem requires a solution that ignores the fragility of the connection. The team must treat the casemate not as a ship, but as a loose pile of debris that must be grabbed all at once. The geometry of the T-rails, which was designed to deflect solid shot, now acts as a mechanism for structural failure. Every lifting plan is analyzed against the friction coefficient of wet iron on wet iron. The engineers realize that they cannot lift the Georgia. They must clamp it. They must use a force that exceeds the tendency of the rails to slide apart. The delicate touch of the survey divers is finished. The operation must now pivot to pure mechanical power. The shift in strategy is absolute. For months, the operation has been defined by the quiet breathing of divers and the gentle, tactile survey of the river bottom. Now the site becomes an industrial construction zone. The time for surgical precision has passed, and the engineering team initiates the phase of heavy mechanized recovery. The salvage barges move into position directly over the wreck site, anchoring against the current, with steel spuds driven deep into the riverbed. The primary tool is no longer the human hand. It is the crane. The objective is to remove the massive sections of the iron casemate that have endured since 1864. These are not small artifacts that can be dropped into a wire basket. They are structural monoliths, built for war and now retrieved like industrial cargo. The largest target is what the team calls the West Casemate, an agglomeration of railroad iron and timber, a single mass in the tens of tons class. To lift it, the salvage team must overcome two distinct forces. The first is gravity, which acts on the sheer weight of the metal. The second and more formidable force is suction. The suction is embedded in the dense clay of the Savannah River, which can hold the object with a grip that rivals its own weight. If the crane pulls too quickly, the suction may refuse to break and the rigging can fail under a shock load. If they pull too slowly, the current can shift the barge and drag the lift offline, destroying the integrity of the artifact. The solution is a calculated application of brute hydraulic power. The crane takes the strain and waits for the critical moment when the clay releases its hold. It is not a clean lift, it is a slow tearing of the river bottom. As the casemate breaks free from the mud, it releases a cloud of silt that blacks out the entire sector. The massive section rises through the water column, a dripping wall of corroded iron that has not seen sunlight since 1864. For the smaller debris, the method changes to the mechanized grapple. This is a heavy hydraulic claw suspended from the crane designed to close with thousands of pounds of crushing force. The operator drops the bucket into the designated grid squares, where the casemate has collapsed into loose piles of rails. There is no diver in the water to guide the jaws. The operator relies on the coordinates mapped during the touch diving phase and the sensors on the crane. The bucket descends into the black water bites into the riverbed and closes. It rises to the surface, streaming mud and water, revealing a tangled knot of T-rails, timber fragments, and river debris. It is a violent extraction that prioritizes clearance over preservation, but it is necessary to meet the depth mandate of the harbor expansion. The scale of the removal is staggering. Over the course of the heavy lift phase, the team brings roughly 440 tons of material to the surface. The deck of the salvage barge becomes a graveyard of Confederate iron. There are twisted rails bent by the impact of the scuttling. There are sections of steam machinery that never had the power to fight the current. And as the work continues, the river bottom that was once a hazardous obstacle course of ordnance, and iron is documented, sorted, and cleared from the channel footprint. The channel is brought to the required depth, ensuring that modern container ships can pass safely overhead. The heavy lifting is complete. The casemates are secured on the deck, and the mud is washed away to reveal the details of the construction. The recovery is a success in terms of tonnage and engineering. But within the recovered pile are objects that tell a more personal story. The team has recovered the cannons of the Georgia. These guns are not just heavy tubes of cast iron. They are the primary evidence of the crew's mindset on the night of the loss. The engineers turn their attention to the muzzle of the large Dahlgren gun and prepare to look inside. The 9,000-pound Dahlgren gun rises from the river on a heavy lifting sling. It is a massive cylinder of iron coated in a thick layer of concretion and mud. To the casual observer, it appears to be a standard piece of 19th century artillery. But the salvage engineers and the naval historians know this weapon holds a final secret. They do not stare at the exterior, they look into the bore. And inside they find not a clean empty tube, but hard evidence of denial. The gun was deliberately rendered unusable before the water took the ship. This is the evidence of a spiked gun. Spiking is deliberate denial. A crew ruins the vent and ignition path so the charge cannot be fired. On the Georgia, it reads as intent, not panic. They could not destroy every heavy piece outright, so they made sure it could never be turned and used. The disabled bore fixes the timeline of the scuttling and the mindset behind it, a controlled demolition of capability. It is the physical signature of the order to abandon ship, locked in iron since 1864. With the recovery of the guns and the removal of the casemate, the primary objective of the mission is achieved. The river bottom where the ironclad sat has been dredged to a uniform depth of 47 feet. The modern Supermax container ships that drive the economy of Savannah now pass directly over the site with feet of clearance to spare. The hazard to navigation is gone. Selected artifacts from the 440 tons of recovered material are transported to the Conservation Research Laboratory at Texas A&M University, where they undergo electrolysis to stabilize the metal. Thousands of other recorded artifacts are returned to the riverbed after documentation and study. The chlorides that have soaked into the iron for a century and a half must be drawn out slowly, or the metal will crumble to dust. The T-rails that were paid for by the Ladies' Gunboat Association are no longer a jagged trap for divers. They are artifacts that reveal the desperation of Confederate naval engineering. The salvage of the Georgia represents the successful resolution of a 150-year-old problem. The Army Corps of Engineers removed a lethal threat from a working harbor without destroying the historical data it contained. The divers who worked in the black water and the technicians who handled the live ordnance neutralized a submerged ammunition depot that had blocked the channel since the Civil War. The vessel was built to be a stationary fortress, a battery that would not move. In the end, she was moved piece by a generation of engineers who understood that the only way to honor the history was to bring it into the light. The river flows on, the channel is open, the iron tomb is empty,